Okay, on to questions 5 through 7. So for question 5, it says a CAN node wants to transmit the following data in the data field of a message. Use the table below to determine which binary code will be entered into the data length code field. So we're trying to figure out what goes here in these 4 bits. It's the number of bytes of data, 0 to 8 bytes in the data. So what we need to know to fill this out is, well, how many bytes of data do we have here? And keep in mind they're 8 bits in a byte. So we can look 4 and 4. That's 1. Another 4 and 4. That's 2 bytes. And so what we're going to put into that data field is 2. And 2 in binary is going to be 0010 in 4 bits of binary specifically. So we're trying to fill out that whole length of data. And that means that's what our DLC is going to be for data length code. And that's it for question number 5. So on to the next one. This is true false. So just answering some basic questions about CAN. Answer the following question about CAN security and vulnerabilities. First, CAN was developed to prioritize speed rather than security of communications. That's definitely true. CAN is really meant for situations in which you have total control over the system. It's expected to be for internal components like the internals of a car to be able to communicate, or otherwise industrial equipment, things like that. And so it's not expecting to have anything be bad or a malicious actor to be on the CAN bus. You're expecting that it's all stuff that's sort of physically connected via wire, and that you can't get into it. Now, that's been proven wrong with things like cars that you can access remotely and then spam or spoof messages over the CAN bus. B, so true false, a CAN node could execute an effective denial of service attack by flooding the bus with messages of type 77F. So let's go ahead and pull up our table here from the previous page. And what we need to see here is whether or not a 77F would be usable as a denial of service attack. And if we look at what a 77F would give us, that would be a heartbeat message, which is the very bottom of that chart. And what we know about CAN bus arbitration is that the higher or lower number message prefixes get higher priority. Heartbeat is the highest number message prefix we can have. Therefore, it is going to get the lowest priority on the bus, which means that we can't really deny service by having that there. And then finally, the last question, a hacker must gain physical access to an automobile in order to attack its CAN bus. I just mentioned that for a previous question, but that's false because generally there's some access method like Wi-Fi, and as long as something like that, Wi-Fi or Bluetooth, is connected to the CAN bus, then a hacker would have access outside of that system remotely. Okay, on to number 7. For number 7, we're asked a 5 milliwatt signal is input to a system with a gain of 5 decibels. What is the power of the output signal in milliwatts? So this is, we have 5 milliwatts coming in. We're going through an amplifier of 5 dBs, and we're wondering what our P out is. Now we have a mix of milliwatts coming in and decibels as the amplifier, so that doesn't work. We have to convert one of these values, and since it wants the output signal in milliwatts, the right thing to do here would be to convert the 5 decibels into a unitless value or unitless gain value that works as a multiplier for the 5 milliwatts. So let's take that 5 decibels, and the equation we use for that is if we have AP, unitless gain, we are going to get that by doing 10 to the AP in decibels over 10, which in this case is going to be 10 to the 5/10, and that's approximately 3.16. So we'll take that 5 milliwatts, we would just swap out the 5 decibels there, turn that into 3.16. And when we have an amplifier like this, all we're doing is we have P out is equal to P in times the unitless gain, which is going to be 5 milliwatts times our unitless gain of 3.16, which is going to give us about 15.8 milliwatts. And that's it for that problem, just using the amplifier equations, making sure we're consistent about either being all in milliwatts in unitless gain or all in decibels when we do this calculation. That's it.